All right, just hold all questions till the end. All right, so vector PQ. So in order to show that it's perpendicular, we need the dot product to be equal to 0, right? So, and that has to do with the cosine relationship. Cosine of theta is equal to u dot b over the magnitudes multiplied. And so if the dot product of two vectors is equal to 0, it means they're orthogonal to one another. So I need the vector, the displacement vector between P and Q. So Q minus P. 1 minus 3 is -2. 4 minus 1 is 3. -3 minus 0 is also -3. Just checking my math. All right. Then you have your vector related to the equation. So the line. I don't think I defined it in any particular way. Coefficients A, B, and C. So the coefficients of the independent variable t are 3, 8, and 6. All right, so the dot product between these two can be -6 plus 24 plus -18, which is in fact 0. Therefore, it is perpendicular. Oh, shockingly, I hit record.
Wait, so how do you just get the numbers for vector PQ again?
Oh, the difference between the two coordinates.
Okay, that's it.
Yeah.
So how do you know which one's subtracting from the other?
Doesn't matter.
So what if, like, I accidentally wrote like 2 instead of -2? Like, indirect, would it influence the answer?
As long as you also write -3 and +3, you're fine.
Okay, yeah, cool. I figured. I'm just making sure.
Yeah, if you leave the other ones as is, you got a problem. Number 2, find the intersection of the plane with the points 1, 2, 0 and the normal vector 2, -1, 4. So the intersection between that plane and the line with the points 0, 0, 0, which is wonderful, and 1, 2, 4. Right? So the plane, normal vector multiplied by x, y, z, so 2x minus y plus 4z equals normal vector multiplied by the coordinate 2 times 1 plus -1 times 2 plus 4 times 0. 2x minus y plus 4z equals 0. All right, so that's the equation of the plane. You could verify or at least do a quick spot check. Plug in your coordinates, see if it checks out. Okay, plug in a 1 here, a 2 there, and a 0 there. It does in fact give you a 0. So at least at a minimum, you know you have a correct relation. It's possible you made like 5 different unique mistakes that checked out, but you know, of course not 0. The line with the point 0, 0, 0, 1, 2, 4. So in order to find the equation of a line, it's again x equals x sub o plus ta, y equals y sub o plus tb, z equals z sub o plus tc. All right, the ABC is the vector, the displacement vector between the two coordinates. So ABC is going to be equal to 1, 2, 4. My x sub o, y sub o, z sub o, well, that's nice. Those are all 0. So I'm looking at just t, 2t, 4t. All right, as my x, y, z. Now, if the line is going to intersect with the plane, then the x values have to be the same, the y values have to be the same, and the z values have to be the same. So that allows me to substitute the values that make up x, y, and z from my linear equation into the equation of the plane. So, t equals 0. So the intersection of the plane would occur at when t is equal to 0, which would mean it's occurring at the origin, right? Because t is equal to 0, but x is equal to t, so x is equal to 0. Y is equal to twice t, 0. Z is equal to 4 times t, 0. All right, so it looks like this line is going right through the plane at the origin. That being said, a visual representation of this might actually kind of, well, we knew that this one was going through the origin just based on the fact that one of the points was the origin. We knew that this point at least was in the xy plane because z is equal to 0. But that normal vector, where is that point? That's the question. So, I guess it's not guaranteed based on the structure. So, yeah, it's worth doing the work, but sometimes you could just grab it from a geometric sense. All right, so the part 3, number 3, the linear transformation is going to reflect vectors over the line y equals x, and then reflect it about the x-axis. So we need the standard matrix of t, and then determine whether the linear transformation actually exists. There's two ways to determine if the transformation exists. Sorry, not the transformation, the inverse of the transformation exists. One way would be to actually find the inverse. If it exists, it exists. The other way would be to find the determinant of the 2 by 2 matrix. Because the shortcut rule for a 2 by 2 matrix inverse is 1 over AD minus BC times the matrix. And the AD minus BC part of it is the determinant. So if you get a determinant equal to 0, 1 over 0 would make it undefined, and therefore the inverse would not exist. Right? So that's something to keep in mind. It's a nice little shortcut, because if you're looking only if it exists, just establishing whether the determinant is equal to 0 or not is probably all you need. Now, if it's asking specifically to determine what that determinant is, that's a different story. You actually have to go through the process. So, reflect over the line y equals x. So here's my I, here's my j. Here's the line y equals x. I mean, if you know all the shortcut matrices, by all means use them, but I like doing it this way. It's visual understanding. The idea is, if you perform the transformation, where do you want I to go? Where do you want j to go? If you're doing a rotation, where do you want them to go? Rotations, again, are based on the unit circle. So there was a reason why I gave that quiz. If I wanted to do a 225-degree rotation, you need to know what the coordinates are at 225 degrees in order to make it happen. Right? Assuming that the question requires you to put it in an exact form. Anyway, if I'm reflecting over the line y equals x, x and y get swapped with one another. So I goes to j, and j goes to I. All right, so if we're doing a reflection over the line y equals x, my standard matrix, normally I followed by j, 1, 0, 0, 1. Now, I'm just going to go the other way around because the their positions have been swapped. All right, so I is at position 0, 1, J is at position 1, 0. All right, now if I want to reflect over the x-axis, you have two choices here. Because matrix multiplication actually performs a transformation. So you could actually find the standard matrix for just the reflection over the x-axis and multiply by the matrix for the reflection over the line y equals x. Or you can take your new, because this is a compound transformation, you can take your new matrix or your new positions of I and j and perform the transformations on those. So I think that's probably the better way to do it if you're doing it visually. So here's my I, which is not that letter, force of habit. And here's my j. I'm reflecting vectors over the x-axis. If I reflect over the x-axis, j is going to stay where it is, but I is going downtown. All right, so this is my new I, and my new j. My new I is at 0, -1, or my newest I. My new j is at 1, 0. All right, so we're good there. Does the linear transformation t inverse, the inverse of t, exist? So what I want to know is what is the determinant of 0, -1, 1, 0? Or again, you could just write it as this with the absolute value brackets. Either way, it's not bad, right? Diagonal down minus diagonal up. Result is 1. If determinant is equal to 0, then inverse does not exist. It's not invertible. I don't think you need me to write that, though. It's a singular matrix. And again, just a quick justification on that. Our shortcut rule is 1 over AD minus BC. DB. DB in this room. This part here is the determinant of A. If it's equal to 0, then my inverse shortcut is undefined, so therefore it does not exist. And this is the proof. I mean, it's a shortcut, but it's not a conditional shortcut. It's not something that works only some of the time. This comes from our process that is the definition of finding the inverse of a square matrix. So if it doesn't satisfy this, it's not a thing.